All right, so let us now assume that we have the similar equation, stoichiometric equation, that nu a plus nu a of a and nu b of b plus everything is going into products. Now, if we find that the rate law follows a first order with respect to a, then the rate, which we can write it as 1 by nu a dA dt with a negative sign. It is first order with respect to a, and or rate constant I'm writing as k prime. And then what you can also do is that you can actually absorb this nu prime into k, and then you can redefine a new rate constant, and then we can just write dA dt is nothing but k into a with a negative sign, and then we can just arrange the terms. dA by a will be nothing but minus k dt, and then we can integrate it to get the integrated form of the rate law. And we are saying that okay, fine, you go from 0 to some time t, and initially suppose I have a concentration like a0 which is going to a, and you know this first order rate equation, what is the integrated form, when you did the radioactivity. So that also follows the first order rate equation. So we'll have ln a by a0 is minus kt, or you can write it in terms of the exponential form, where you'll have a is nothing but a0 into e to the power minus kt. So if you plot ln a by a0 versus t, then you'll have a linear slope, where a linear plot where the slope will be equal to minus k. So this is a plot of ln a by a0, and this is a plot of say versus t. Versus if you had plotted the other way, like you are plotting say a by a0 versus t, and that's the exponential plot, and initially at time 0 it will be 1, and then it decreases exponentially with time. Now you can ask this question, okay fine, what about what is the time at which the concentration drops to its initial concentration, that we call as half-life. You know that, and to get the half-life you just use this equation and put the condition at t equal to t half, the concentration drops to the half of this initial concentration. And you already know that this t half will be nothing but ln2 by k, which ln2 is 0.693 by k. So for first order reaction, we see that the half-life is independent of the initial concentration, which is very important, which means suppose this is 1, suppose this curve starts from 1, so at what time it comes to 0.5? So we say that okay fine, this is the time where it comes from 0.5. Now suppose you start that as your initial concentration, which is 0.5 in this scale, and then you ask at what time it goes to 0.25. you will find that time is also the same time, t half. Or if you start with the 0.25, then you ask at what time it goes to 0.125. you'll find that is also the same time. So the t half is independent of the initial concentration. You could also start from any arbitrary time, not like 1, 0.1, 0.25. You could just start from say 0.8 and ask this question, okay, at what time it goes to 0.4? If I start my initial time at when the concentration was or the relative concentration was 0.8. So this is very interesting, and this happens only for the first order equation. Now for any other equation where actually you have a rate law, which is something like 1 over minus nu a into dA dt, suppose it varies with the a to the power n, where n is not equal to 1. So then we can easily integrate it, and as before we can actually absorb the nu a inside k prime to redefine a new constant k, and we can just write it dA by a to the power n integrated, that will give me minus kt, and when time equal to 0, we're using the same notation. Initial concentration was a0 and time t it is a. So this integration is nothing but ln 1 over x to the power n is nothing but not ln, integration of x to the power 1 over x to the power n is nothing but x to the power minus n plus 1 divided by n plus 1, minus n plus 1. So you can easily write it down, and you can also just write the you can rearrange the terms, and you will figure out that the final form I'm writing here, so it will be 1 over a to the power n minus 1 minus 1 over a0. We are writing a0 like this, to the power n minus 1. That will be, or we can also write it as 1 over n minus 1 here. That will be equal to kt. Of course, this is true for n not equal to 1. This is true for any order reaction, like second order, third order, something like that, provided the second order, third order, or fourth order, whatever we are saying, it is dependent only, the power is dependent only on one species, which means the molecularity is only 1. Now we could have a second order. If it is second order, for example, this n equal to 2, then we'll have a rate expression something like 1 over a minus 1 over a0 is kt. That's it. Now you could ask what will be the half-life for any such reaction where n is not equal to 1. Now you can easily figure that out. Instead of a, I'll just put here a0 by 2 raised to n minus 1, and you can see here that the value will be 2 to the power n minus 1 minus 1 divided by n minus 1 into a0 raised to n minus 1 into, of course, you'll have the rate constant here. Now you see here that this is true for, again, n not equal to 1, which means for second order it will be 1 over a0, for third order it will be 1 over a0 square, which means now the half-life depends on the initial concentration. So this is a very striking difference between the concentrations for the first order reaction with any other nth order reaction. Now this equation we got when actually the rate is proportional to the concentration of a squared, but you could have a second order reaction where it will be something like a into b. So the two species are actually coming. So the question is, how will you solve it? Similarly, you could have a third order reaction, and instead of a cube, it could actually be a into b square, or something like a into b into c. How will you solve those equations? Now what we are going to do right now is that we are saying that, okay, fine, let us start with the our old stoichiometric equation. Sorry, it will be just a. Nu a plus nu b is going to product, and at time 0 I call this as a0 and b0, and at time equal to t we are saying that, okay, fine, let us assume that the advancement of this reaction is xi. So the amount which is reduced for a will be minus nu into xi. Amount reduced for b, because both are reactant, remember, that will be minus nu b into xi, because that will be proportional to the stoichiometric number. So now what we can write is that the problem here is that if I write dA dt, or minus 1 over nu a dA dt, so the problem we'll face is that it is now some rate constant into a into b. So the b is appearing here, so I have to write b in terms of a, otherwise I cannot solve it. Now I can actually write it very easily. So this is a right now, and this is b. So let us just write it first. So a is nothing but a0 minus nu a into xi, and b is nothing but b0, or instead of since we are solving the a, we'll just keep it as a, because that's a variable here. So not variable, the variable is t, but that will integrate anyway. So we're writing it as k into a, and instead of b, we're just writing it as b0. Remember, b0 is a constant, minus, I can write it as nu b into xi. But what is the value of xi here? Let us see. So what I'm saying here, I know that a is a0 minus nu a into xi. So which means xi is nothing but a0 minus a divided by nu a. And similarly, you can write for b as b0 minus nu b into xi, and you can ask this question, what is xi here? Xi is nothing but b0 minus b divided by nu b. So you can now equate these two equations and write b in terms of a. So that's what we are going to do, and if you do that, so you can easily figure out that I'm skipping the steps. So it will be nothing but nu b divided by nu a times a0 minus a. So now I have an equation which depends only on a. Remember that b0 is a constant, just like a0. So b0 is not a problem. So now I can rearrange the terms and then try to integrate. And then let us see how to do this integration. So I'll have 1 over nu a, and then we can just write dA divided by this entire thing, which is a times, it is basically b0 minus nu b by nu a times a0 minus a, and then we have kt here, and then we'll integrate. So as before, we'll just integrate, we'll say that at t equal to 0, the initial concentration was a0, and at time t, the concentration was a. Now to solve this equation, you can actually use a standard integral, which is dx divided by x into p plus sx. That you can write it as minus 1 over p ln p plus sx divided by x. So that integral you can directly use, which I have provided here, and you just have to identify what are the x, p and s here. So x is nothing but the concentration of a that you are integrating, and you can see it here, a appears here just like x appears here, and then p plus sx. So p is nothing but the constant, and you can see the constant is nothing but b0. If I just write this thing, and it is nothing but b0 minus nu b by nu a into a0. That part is the p, and then you have a s. S is nothing but, if you expand it, so I'll have the third term as a times nu b by nu a. There's a minus sign here, and there's also a minus sign here, so that is plus. So S is nothing but nu b by nu a. So then I can actually right away use this integration or integral. So I'll have a minus sign here. So I already had a minus sign here, so that will be plus. So it will be 1 over nu a, and then 1 over p. P was nothing but b0 minus nu b by nu a into a0, and times I have ln p plus sx. What is p? P is b0 minus nu b by nu a into a0. That is the p. And p plus sx is nothing but what we have written in the so this entire part. So that was p, and then I had nu b by nu a into a, and it is divided by x. X is nothing but a. Now remember, this is just the integral, so I have to evaluate it between a equal to a0 and a equal to a, and that should be equal to, the right hand side integration is pretty straightforward, that should be equal to kt. So kt is nothing but this. So I can now simplify it. So this term, actually, if I just multiply it with this entire thing, so I'll have 1 divided by nu a b0 minus nu b a0, and then I have to take the upper and lower limits. So in the upper limit, when I'm writing a as a, so you remember that what was this entire thing? This entire thing was we actually replaced it. If you remember that it was replaced for b. So this was the expression for b. It was k into b, and the entire thing was actually b. So it is nothing but b by a minus, for the lower limit, if I put a as a0, so then you see that these two terms will cancel, and then I'll only have b0 by a0. So we can again rearrange it a little bit, so which will be nothing but 1 over nu a b0 minus nu b a0 and then we'll have ln, we have b by b0 divided by a by a0. That is equal to kt. So that will be the integrated form for a second order reaction, where it is first order with respect to each of these each of the reactants. So you can see that the moment we go from first order to a nth order reaction, where the nth order is only with respect to one particular reactant, we have a form like this we already discussed. And then for a second order, we see that we have a very different way of solving. We have to use a standard integral, otherwise you cannot solve it. And then you can also ask this question as a homework problem. You can try solving this. If I have a general equation like a plus b plus c, whatever, and if I have a situation like this, 1 over nu a dA dt, how actually, what will be the solution if I have, say, k into a into b square, suppose. It can be a square into b, but that's mathematically the same. Or if it has something like k into a into b into c. Now the procedure is the same. You can first solve this one. You don't need to solve the ABC problem, but the procedure is the same. You just have to eliminate xi from the b equation and a equation, and then equate them, and then write b in terms of a or c in terms of a. So everything you have to write it in terms of a, because you're writing your rate equation as dA dt. If you had written as dB dt, you write everything in terms of b, and then you choose some initial concentration which are constants. But then at the end of the day, you have to have some kind of you need to know how to integrate that particular complicated form, because you need to use a standard integral, a standard table, and find out figure out actually what is this integral, and then use it and solve it. Now, in the next part, we'll discuss some special reactions, like what happens. So far, we are actually considering only nu A plus nu B, all these things going into the product as an irreversible reaction. But what happens if we include reversibility? And then we'll also discuss some special reactions like competing reactions, which are in general called the opposing reaction and the consecutive reaction. Those things we'll discuss.